Well, it turns out that the established protocol for creating classes is the metaclass protocol, and it works pretty straightforward. When we define a class, we can also give it keyword arguments, and a specific keyword argument we can give it, metaclass, gives us an object that will be used in order to construct this class. Metaclasses have two purposes, and beyond that, they just have a lot of details. The first purpose for a metaclass is to give you the ability to implement the Python vocabulary on a type, not on an instance. Let me show you what I mean. When we want to implement the Python vocabulary on some data, for example, we want to implement the ability to use the square brackets or the parentheses. So here we have an object of this type, and we want to say object open close parentheses, well, we implement call. Or if we want to say obj open close square brackets, we implement get item. Or if we want to implement the vocabulary like being able to add these things, we implement add or radd or iadd. This is how we implement it on an instance of this type. Well, if it's the case that we want to implement this on a class itself, so we want t to be callable. Well, it already is. I wonder where that actual call method might sit. But if we want to implement open close square brackets, or if we want to implement t plus t or t, how do we do that? Well, naturally, we have to go one slightly level higher, and we have to implement it on its metaclass. So the very first use of this metaclass is basically just give us the ability to implement the Python vocabulary. Here, let's do that. And let's implement add, and we'll implement or. And you can see, there we go. Now you might wonder, how on earth could this be useful? This seems very bizarre. I've seen some of this in maybe some of the type hinting DSL, but where does this actually show up in other code? Understand that if you're a user of the enum module, you might wonder, why do I use the enum module? Why don't I just use a typing.literal or a string? But one of the benefits of the enum module is if I define my choices as a typing.literal. So I have a function that takes a choice, and I say it's a literal A, B, or C. Well, this is pretty nicely documented. Somebody can see that it's one of those three values. My type checker can check for this. Everything's great. But if somebody says, I want to have a random choice, I want to choose one of these randomly, well, they have to repeat what the choices are. And if you add another choice here, they have to make sure that they change this code. Whereas instead, if you use the enum, we get a structured type, and if we look at the enum, the type itself can be iterated over. And thus, we can say, give me a random one of these values such that if these values change, any subsequent code that is reliant on those values changes automatically. There you go. So this is one of the advantages of the enum. We added some data structuring for some purpose. The purpose was so that we could access what all the elements are by iterating over this thing, either explicitly here or implicitly as we passed it to this random.choice. So that's moderately useful. The other thing that a metaclass can be used for is asserting constraints from a base type to a derived type. And just like we see when we talk about things like property and the descriptor protocol, it's always valuable for us to understand how these things work, because we may discover that in the Python standard library, there are tools that are first-order approximations that are genuinely helpful for us, but they're just too they're too general or they're too specific, and we can do something better in very little code. And so, if I wanted my derived type to be certain to implement a specific method, here we'll call this method G, and it's necessary that you implement that, otherwise this code is incorrect. What I could do is I could add a metaclass to the base, like this, and I can hook into how classes are constructed, there's a new and an init on the class itself, just like there's a new and an init on the instance itself. This takes the name, the bases, and the body. I actually get the pre-constructed type, unlike in build class where I get the fully constructed class. I get the class prior to construction. So here I actually get to look at the scope. I get to look at the namespace of the body of this class, but not the fully constructed derived, which could be valuable because maybe I want to change some things, or I want to see if you affirmatively define something or not, or whether something might have been added by another means. So here, let's add this in. And of course, I'll skip any other additional keyword arguments here. We'll dispatch this to the actual established protocol. There we go. And you can see I have a hook point on just the base and the derived. And so I can say if G not in body, raise type error must implement G. Now, of course, this is going to hook at this point as well. So here I might have to say def G like that in order for this to pass. And I could even do something very similar to that abstract method. I could just do something like this. Like that. And I could maybe even iterate over the bases and then identify what all the abstract methods are and then check that they exist. Note, I did this in very little code. And in addition to what the ABC module in the Python standard library can do, I can even check that the signature is correct. So I could look at the signature of this thing and say, oh, you implemented it, but did you actually implement this as a callable with the parameters that I expect, or with some documentation, or with some other fields that I wanted you to have? If not, that also isn't, it just simply isn't good enough for me. I can do a lot of stuff in a very, very small amount of code that is actually much richer in terms of the correctness. And note, I didn't instantiate this object, unlike the Python standard libraries abc.abc or abc.abc meta. This will ensure the correctness of this code, not just the correctness of instantiations of this object, mechanism that I want. Now, note that this is inherited down the class hierarchy. So if I have another derived, like this, well, here you can see I can also check that this derived, let's even implement it from here. I can also check that this thing has its own unique definition of G, not a definition that it pulled from some previous level. So I can make that distinction if I so choose. And anything that continues to derive down this path will have these checks enabled. The problem is, if something here itself has a metaclass, it is very easy, given how obscure metaclasses are considered to be, for somebody to do this incorrectly. And for example, for the metaclasses to have, this issue where we have a non-strict subclass of the metaclass, or if I have some sort of multiple inheritance, for us to have some oddities here, whereby let's do a derived 3 with 2 bases, and this thing will have its own metaclass. And this is like this. And here we'll turn this off for a moment. And you can see here again, for us to have some oddities here where we have 2 bases where the metaclasses don't align. So the metaclass approach is very powerful. And there's one thing that it uniquely can do, gives us the access to the Python vocabulary. But in terms of enforcing these constraints, I don't know how much I'd rely on it, given all of these sharp edges. It is a broadsword, not a nuclear bomb, but I'm looking for something maybe a little bit more surgical and a little bit safer for me to use, and instead I'll use an even better protocol, an established protocol, the init subclass protocol. Init subclass is basically the core of the idea of the metaclass. That is, when you initialize a subclass, give me some hook point in a way that we can actually reason about that doesn't have all of these other sharp edges. It is very surgical. So if I do init subclass here, And let's show you this. There we go. And note, I'm not required to return anything here, just like a normal init. It just allows me to modify the body of this class. Note, this is only triggering on the subclass. It doesn't trigger on the class itself. But note, it also gets the fully constructed class. So, for example, I wouldn't be able to distinguish between cases where something was implemented locally versus implemented because it was pulled from, the MRO. That's not strictly correct, because I could actually maybe try and figure out where G comes from. So here I could say if not has adder G, erase some error. Otherwise, I could do something like class.g, and I could use the class method of this, or I could use the inspect module. I believe it's like get. Maybe gets, there's probably something in the inspect module that does this, but I could just kind of do it like this. So I could kind of peek to see where this thing comes from, and then see, and that's that. Here I need to figure out what class this is implemented in. There is a way for me to figure this out. If not directly from this thing, then I'd figure this out by trawling the MRO myself. So here I could do this for class and like this. And I could see base class. And this is basically where this thing came from. And of course I'd have to check to make sure that this thing actually exists, so here, something very simple. So I could kind of check, but this is very imprecise. And I can think that there are a couple other considerations I would need in order to really make sure that this just works. But otherwise, I have a very easy way for me to just add in these hooks to check things. And I can do what the ABC module does, even better than the ABC module itself, in very little code. I really strongly encourage you to use init subclass as much as you possibly can. Anytime you create a base class and somebody could derive from that, put a couple of checks in the init subclass. Don't be too coercive about it. Don't force them to do things they're not going to want to do or things which they don't strictly have to do. But at minimum, if you have some guidance, you must implement this, this, and this, add an init subclass. And it's just as easy as can be with very clear, very simple code that has a rich set of checks that you can perform constructively, not on instance creation, but on class creation. Let us take a look at the last mechanism that we'll discuss. Let's talk about not class methods, let's talk about class decorators. When we talk about class decorators, it may be difficult for us to distinguish class decorators from the init subclass approach. Because when we talk about class decorators, what we're doing is we're writing a decorator that basically applies to a class. Remember, whenever we have a decorator in Python, it really is just a little bit of syntax here. Here, if we have a decorator that looks like this, applied to a function, we know, and we're more or less guaranteed, that these lines of code here are equivalent to the following. It really is just turning an f equals decf, a name binding, plus a function call into a single line of code that looks like this, that's placed slightly differently. In a very similar sense, if we do this on a class, well, basically, we're getting the same thing. Here, there really is no major difference. So if we think about that, we might think, okay, if I wanted to have some init subclass that constrained a derived type, and I wanted to have some class decorator that constrained a derived type, what would the difference be, and why might I choose one versus the other? With the class decorator approach, it would look like this. So if this thing doesn't have some implemented method, we'll raise a type error, must implement f. Otherwise, we'll just return the thing back. Here, this doesn't meet our constraint, so we can add in that f method, everything's fine, or we could do this. And here we go. And we'll call this derived in this case, because here we have a strict base derived relationship. There we go. If it doesn't implement, we get an error. and if it does implement, everything is fine.